Welcome back. Welcome back. Welcome back. Good morning, good afternoon, good evening, and good night. Just kidding. That intro is kind of lame. I'm not going to ever do that one again. But welcome back. What's good, you guys? Um is that intro from something? Is it I feel like it's from Spider-Man or something like that. I might be making that up. Can I say that in this video? Is that like copyright? I don't know. I should probably look how copyright works if I'm going to be a YouTuber, huh? Anyway, today we're gonna talk about doing experiments. And I'm gonna be straight up with you. I am notoriously disinterested in experiments. Um, let me ramble at you for a moment, and then we'll talk about experiments. In physics, when you get to college and you tell them you want to be a physics major, you want to be a physicist, they kind of roll their eyes at you and then begrudgingly induct you into the field and then sign you up for some classes that you're probably woefully underprepared for. But you know what I mean? You're enthusiastic and it's the spunk that counts. But once you turn into a physics major, you hear about this dichotomy of theoretical physicists and experimental physicists. So these are the two. This is not actually how it's broken down, but in the mind of young aspiring physics major Barton, those are the two fields, right? There's theory and then there's experiment. Uh, some nerds sit in a closet all day and they think about math and they draw pretty pictures and they do hard equations and they physics with their brain. And then some other nerds sit in a different, bigger, insulated closet with a bunch of really expensive, high pressure cables and they shoot lasers into boxes with stuff in them and then photons and neutrons and other words that I don't know about come out and then physics. I always wanted to be on the theory side of things. I didn't want to, get bogged down with nonsense like real life and reality. You know what I mean? I wanted the pure stuff. That give me that good physics. But uh I found out I think most physicists are actually experimental physicists. Um but you know what I mean? I'm a math teacher. What do I know? But you notice I say I'm a math teacher, not a physics teacher, right? I've always way preferred rolling up my sleeves and doing some good old math. Slopping all over a table, really digging my pencil into that stuff, doing some integrals, thinking about derivatives and boundary condition. Oh, the good stuff. I'm salivating just thinking about it. And I never really liked experiments because they never work out the way you want them to, right? You do them and you're like, this didn't work. What am I supposed to learn from this, right? So, short story long, I feel like because of my own bias, I do a woefully inadequate job of talking about experimentation, experiment design, data measurement, and all that stuff that no one cares about in this class. But today, we take our first step at change and growth and adjustment and realizing we need to be better for our students. And also, you know, it's on the test. So, we're going to talk about experiments today. So, what we're going to talk about today, we're not going to get real bogged down. I looked at some practice problems and I went, woo, they want them to answer those. And then I decided that, you know what, let's talk about what can I even do experiments with? Like, what are the tools? What are some things that I should be thinking about when I'm setting up an experiment? What are some conditions? You know what I mean? What's the introduction, the body, and the conclusion to my paragraph? What's the important meat and potatoes that the AP graders are looking for, right? keep in mind, these experiments, they probably work in like a physics lab, but you're also learning from a person who never got the opportunity to work in like a real big kid physics lab. I took labs, right? But they're all like nice and contrived for the they're nice and contrived is what I'm getting at. So I'm going to teach you how to answer contrived lab questions. When you want to do real big kid physics, ask your professors in college. Okay, a second aside before we dive into this. The first thing you should do as a freshman in college, if you are going to be a math, science, and I'm not 100% certain about engineering, but math and science, so like physics, biology, chemistry, whatever science you're into, right? Psychology. As a freshman in college, you need to send an email to your professors and say, hey, professor, write this down. This is part of your notes for today. Say, hey, professor, don't say I'm new around here, but this is my first opportunity to talk to a researcher. Can you tell me about what it is you research? And if, first of all, you're their new favorite student, there's nothing doctors love more than telling you about what they research. It's like being vegan. You know what I mean? Doctors in universities can't walk into a room without being like, and then my field of research is actually face-centered cubic crystals in sodium chloride nanotube. You know what I mean? And they'll go on and on. They can't wait to tell you what their favorite shtick is, what they research. They love that stuff. They've spent the last 30 years looking at face-centered cubics, and they are just, you know what I mean? A kid asking them what they research is their wet dream. Is that vulgar? I'm sorry. I apologize. I'm not editing it out, but I'm sorry. Apologies. Sorry. I shouldn't say things like that. But ask them. And then if you're interested, say, wow, that sounds really, really interesting. As a freshman, is there anything that I can do to be involved in your research? Do you have a spot on your research team where I could get some experience in a real lab? And that will take you so much farther than taking these 3 credit classes. That's the real stuff if you want to be a scientist or a mathematician. You want to get in with a professor and have them show you how to do research, because it's completely different from what you actually learn in any classes. And now I'll get off my soapbox. Okay, let's talk about how you answer AP test questions about designing experiments. So the first thing we need to talk about, because you have been in your house the entire time this semester, you haven't gotten the opportunity to blow stuff up and break stuff and throw stuff across the room, right? So we need to talk about what are the tools? What can I experiment with, Mr. Barton? So here is a non-exhaustive list, meaning there's some stuff that's not on this list that you should probably assume is in a physics classroom. We'll talk about that at the end of the slides of the tools of the trade, but here's some common stuff you should be aware of that is not necessarily in every room of every building on Earth, right? So, of course, we have a meter stick and a measuring tape, okay? These, if you think to yourself, man, I wish I knew how far that was or how long that was, these are your tools. These measure linear distances very, very well. Measuring round distances is harder. Measuring tapes can get the job done, but in general, I don't think you're going to be asked to measure round distances unless they're perfect circles, which this thing is not. But in which case, you just measure the radius and then, C equals 2 pi r. And that'll get you there. Cool. Other things that are in a physics classroom, Timers and stopwatches. Cell phones can be used as such. Most cell phones come equipped with that equipment now. They measure time in seconds. Okay. Just like chemistry labs, we have triple beam balances. Some nice labs have electronic balances, like what you use in like kitchens and stuff. We don't have those at our school. We have these. But if you need to know how heavy something is or how much mass something has, these will tell you the mass in grams. Okay. The first thing that we have that may be unique to a physics classroom, there are two variations of this. There are spring scales, which is exactly what it sounds like. It's like a little box, and it's got like a little doohickey here, and then it's got like measurements here. And then there's a spring, there's like a little window here where you can see, and then there's like a spring inside. And then there's a hook down here. And you can hang something on this hook, and this thing on one side of it, it will tell you mass in grams, and on the other side, it will tell you force in newtons. So spring scales are dual purpose. They can be used to find mass because there's usually a scale for that. But these are the most generic, commonplace force gauges that you're going to see. And you can use them to measure forces, but they only measure forces in that direction. They're linear. They can't tell you, like, if your force is going this way, it's only going to tell you that component of it, right? So you got to be a little careful. They're very linear. Then there are digital force gauges, and these are boxes with a hook on them. And I've seen some where they have the display right here. More commonly, they plug into a computer with, like, you know, a keyboard and your tower and whatnot, right? But they plug into the computer, and then they can give you like a force as a function of time graph. So those are very nice. Again, they're linear, and they only measure that direction. Some nice ones also measure that direction, but they're very linear. They measure how hard you're pulling on something typically. You can also assume that any physics classroom is also a math classroom because not enough kids take physics, and most physics teachers have to come to reality and realize that they're probably going to end up teaching math in addition to physics. It's just the way of the universe, you know. But because of that, luckily you guys also get protractors, rulers, compasses, calculators, etc. So that's some other stuff you can kind of assume is in the classroom. Okay. These are some of the most important tools. Okay. So far, things that you can measure with these tools are distance with a meter stick. You can measure time with a timer. What else can you measure? Mass with a scale, and force with a force gauge, spring scale or force gauge. So this pretty much covers everything you've learned so far in this class, right? If we want to know velocity, that's change in distance over change in time. I can measure both of those things. If I want to know velocity, acceleration, that's change in velocity over change in time. And I can measure velocity with these things, right? So, you know what I mean? Pretty much everything that you care about so far can be measured with these four tools, with a meter stick, a timer, a scale, and a slightly different scale. Okay. Here are some other really like nice things that you can find in physics labs to help you get the job done. And I think there's actually one more that I want to talk about that you've seen before in one of our virtual labs, but you haven't seen probably in person yet. So one new tool is a motion detector, sometimes called an ultrasonic locator, if you want to be pretentious and impress your parents and convince them that you deserve those new Nikes that you really want. This thing is, let me draw you a picture. The one that I have kind of looks like this. It's like a box, and it's got like a thing on the front, and it goes like that. And this thing shoots out sound waves, and they bounce off solid stuff like boxes, right? And then these sound waves come back, and then this thing listens with its fancy ear, right? And it hears these sound waves, and it counts how long it takes for these sound waves to come back. So it will tell you the distance between the detector and the object. This is very, very handy because it's a meter stick. It tells you a distance. But this thing also plugs into your computer. CPU, I guess. I don't know. And you can get some really, really nice, useful graphs with this. You can get a position versus time graph. And this is handy because the slope of this thing is velocity. And because it's plugged into a computer, the computer can do some really great math for you and it can measure the change in distance over change in time like 100 times a second. And then it can make for you a velocity versus time graph with real-time velocities. And because velocity versus time has a slope of acceleration, it can also tell you acceleration versus time graphs. So this is a very versatile tool if you care about the position, the speed, or the acceleration of anything solid that sound waves will bounce off of. If they give you a ball of cotton, that is probably not going to work. If they give you something really small, like a toy car, like a Hot Wheel, that also probably won't work. These things are not super duper sensitive, but you get the idea. Okay. There's also low friction carts, pulleys, things like that. Like the puck lab we did. They're not pucks, they're carts. They're like little toy cars that roll on this nice metal track. They're pretty nice. Pulleys, these are usually low friction. Like you know what I mean, a pulley, like a pulley, like just a wheel that turns ropes. You wrap ropes around to change the direction of a rope. They're cool. Masses of various shapes and sizes. These AKA are weights. So if you need different weights for stuff like stretching springs, weighing down carts, throwing at people, I don't know, all kinds of stuff. They're very useful. They come in various sizes. Usually there's like a 10 gram, a 50 gram. I think there's probably a 25 gram. You know what I mean? Like kind of this increment. There's hundreds, there's 200s, and then they skip up to 500. And then there's like a 1 kilogram one that I have laying around my room somewhere. Okay. Usually we have springs of various constants. None of the constants are labeled, but there are springs in case you need them. And then there's random junk that you can find in like hardware stores, like string, tape, towels, toasters, thermometers. You know what I mean? Like if you could probably find it in like a somewhat handy person's garage, you can probably find it in a physics classroom. So that's some stuff that exists that is available to you when you're being asked to design an experiment. These are things you can use to measure with. Let's talk about things that don't exist. Okay, tools that do not exist. And I only include this because one year when I was teaching, my students took the AP test and they came back and they absolutely did not tell me about the AP test because it's forbidden and they're not allowed to tell me what's on it. But I read some memes on some stuff, and there were some memes about kids saying, to measure the coefficient of friction, I use a frictiometer. It's just a tool that measures friction, the coefficient of friction, right? This tool does not exist. 90% of the time, if you're being asked about this thing, it's because that's the thing you're being asked to measure in the problem. So what they want you to do is, measure the mass of something and do something with like normal forces and Newton's second law to measure that stuff. There is not a frictiometer. My students definitely didn't come back to my class and definitely didn't tell me that they said use the frictiometer. And I definitely didn't feel a sinking sensation in my heart like I've let them down. But, hypothetically. There is not an energy-ometer. Like there's not a thing you can point at something that says, yep, 27 joules. That doesn't exist. Yeah, that doesn't exist. Let me try and explain to you why that doesn't exist. Energy, I don't know if you've noticed, but this is very, very, very dependent on sort of your frame of reference, right? Let me show you an example. Let's say you're sitting in a chair. Right, that's you. And you're holding a ball. And you're super happy about it because you love holding balls. I'm sorry. I'm a child. You love holding spheres. And okay. And let's say it's, I don't know, 1 meter off the ground. And it's got a mass of 0.1 kilograms. How much energy does this thing have? You're sitting still. Okay. Well, it's got potential energy because it's a meter off the ground. So, UG equals mgh 0.1 times 10 times 1 is 1 joule of energy. Right? So now you say, Mr. Barton, this sphere that I love holding so much has 1 joule of energy. Okay, now consider this. What if I told you your chair wasn't a chair at all? Oh no, it wasn't a chair the whole time. But instead, your chair was a seat in a car. Now it's got kinetic energy because you're going 90 miles per hour on the freeway, right? But to you, sitting in your chair holding your sphere, it doesn't look like the ball's moving. It's at rest for you, right? And wait a second, what's that? Your car is on planet Earth and it's rotating around the sun at hundreds of probably maybe not hundreds, maybe tens of thousands of kilometers per second. You're flying through space. So this ball has millions of joules of energy because you know what I mean? You get the idea. To you, it's not moving. To someone standing on the sidewalk, it is moving. To someone floating in space, right? And they've got like a helmet on with a little tube, right? It's going hecka fast. So energy is very dependent on your frame of reference. So something that you say has no energy might have 1,000 joules of energy to someone else. So you can't really point a tool at something. It's something you calculate. Okay. Power meters do exist. These do exist, but not really in a useful way for a physics classroom. Right? Like a dynamometer, I believe is the correct term. The thing that they test cars on to tell how much horsepower they have, those are power meters. But these are things that you like hook up to something that spins, and then it tells you how much energy you're putting into the spinning every second. It's not going to tell you like a conservation of energy thing. They're really not super useful. Bicycle trainers, like the thing that your mom rides in the living room, like in between stuff, watching soap operas. That's a power meter. That's why it costs $500. But you get what I mean. They're not for physics. You're not going to use it for physics. They're not in a physics classroom. Okay, so now that we know kind of what tools we have at our disposal, let's talk about actually setting up an experiment. Okay, so here are 4 very important questions you should try to answer when you are asked to design an experiment. Okay, every single AP test question that asks you to design an experiment should follow this sort of algorithm, if you will. These are the talking points. These are the important things that they want you to say. The same way in English class when they say, what do you think the author meant by this metaphor he made here? Well, he meant that Gatsby is an unreal. You know what I mean? Like, there's certain things you should talk about. So there are certain things you need to talk about for your design of an experiment. The first one is you need to tell me what stuff I got to go get to do the experiment. Okay, you've got to tell me I need a meter stick, I need 3 meters of string, I need a scale, and I need a large caramel macchiato grande, hold the ice, hold the lemon, low soy stat, right? What do you need to do it? And maybe you don't need to say 3 meters of string, but you need to kind of have an idea, right? You got to say, tie the mass to the string, hang it from the ring stand. Okay. Pour the milk from the graduated cylinder. These are all the things you're using. You can't just say, measure the mass with what, dog? You can't just say, you let the ball go and then get the velocity. Get the velocity with what? Are you using a motion detector? Are you using a meter stick to calculate its distance traveled and a timer to record how long it took, and then doing velocity equals change in position over change in time? You need to be specific with what you're using to do that. The second thing that you need to do is tell me, how do you use the equipment, and more specifically, actually not that color, this color. What data do you collect? If you say, let the ball go and get the velocity, get the velocity is way too vague. If you told your 6-year-old brother to get the velocity, they're going to go into the kitchen and be like, I couldn't find it, right? You have to explain how to calculate the velocity, how to measure it with what tools. You can't just say, get it. I don't know how to get it. You have to tell me how to get it. So you have to say, use the meter stick to measure the distance traveled by the ball. Use the timer to time how much time it takes to go from the beginning of the racetrack to the end of the racetrack. And then, once you have very, very specifically told me how and what data to collect, you have to tell me what to do with the data. This could be a couple of things. It could be use it in a calculation. Once you've measured the distance and you've measured the time, use the average velocity formula to calculate them. Here's the formula, and tell me what it is. The other thing you could do is you could say, record the position of the ball every second and make a data table with position and time, and then you plot this data on a position time graph, and the velocity will be the slope of that bad chicken, right? So tell me what equipment to get, tell me what to use the equipment to measure, and then tell me what to do with those measurements. All right, this last one is like a star. Usually on AP test questions, there will be like a little sentence at the end that says, make sure to talk about how to minimize error, okay? This is probably the hardest part of these 4 things to include, because you have to be creative enough to talk about, you have to think about what choices you are subconsciously making. And not every single system has a lot of things you could change about it. I have one on here that is, I think, a really good example for us because it is so, it's something you haven't learned before. So you don't have any background information to goof you up. But how can I minimize the error? Let's talk about that. There are really two ways that you can minimize error. Right. Of course, there's always get smoother bearings, make sure there's no breeze, but that's all cop out stuff. That's like baby stuff. It's like how do you do chemistry better? It's like measure better. You know what I mean? That's not a real answer. It's like how do I get better? Just be better. That's not an answer. In physics, the ways that we can reduce error is by either repeating something a bunch of times and taking an average, or being conscious of other possible variables and making sure that we hold them constant, meaning we're aware of them and we don't vary them. We keep our control variables controlled and we don't spray them all over the place. This one I will talk about a little bit more in depth when we get to the second example. This first one, let me tell you a quick story. When I was in college, I had a wonderful professor by the name of Dr. Culbertson, and we were doing a lab for Dr. Culbertson's class where we had to do, it was like a marble drop or something, and we had to learn some stuff. Anyway, we needed to know the average mass of this jar of marbles, right? So what we did, and I wish you could have seen poor Dr. Culbertson's face as we tried to do this. We took these marbles out of the jar one by one, and we put them on a triple beam balance. And we put it on there and it rolled around and almost fell off. And we tried to get a mass of like 10 of these things. And then we were going to average them, right? We were going to average them. And Dr. Culbertson politely took one of us aside. He goes, let me give you some advice. Put all the marbles on the scale at once. Get a little cup and fill that bad boy with marbles. Find the mass of that. Divide by the number of marbles. And then that'll be an average mass of the marbles. And we were, oh my goodness, you guys. We were going to get a list of masses and calculate a mean. It was so funny. Anyway. You guys ever got to take a trip down memory lane? Me neither. Anyway, so when I say repeat a process and take an average, sometimes there's a clever way you can do it. Like just weigh a bunch of marbles at once and divide by the number of marbles. You don't have to literally average their individual masses. You can find a bunch of mass and then divide it, and then that's the average. We'll talk about that one in the second example too. Really, the second example is like that one, and the first one is the getting your gears going one. Okay, so let's go look at some examples. So a toy car is known to travel at a constant velocity, but the velocity is unknown. Describe an experiment you could do to determine the velocity of the car. And this is an AP question. They're like 6 points. This is an FRQ. The other like 7 points that will be on this FRQ are like weird specific questions. We'll look at them later. We'll do some practice, but all right, let's get the first 6. Okay. These first 6 come from these. These are the 4 really hot topics that they are going to make sure that you use, right? Did they tell me what equipment I'm using? Did they tell me what to record? Did they tell me something about using Newton's second law with that data? Did they tell me to take an average, right? Then points 5 and 6 are, would it work? Did they set up the graph right or something? You know what I mean? They're like specific to the problem. They're probably looking for like the average velocity equals delta x over delta t here or something like that. You know what I mean? But 4 of those 6 problems, which is enough to pass the AP test, are what do I use? What do I measure? What do I do with it? How do I reduce error? Okay. So let's talk about this toy car. When we are trying to design an experiment, we need a target in mind. Okay, we want to know the velocity, and the first place we should start is a little bit of theory. What do I know about velocity? Well, I know a lot of things about velocity. I know an average velocity equation is change in x over change in t. I know a velocity equation is v naught plus acceleration times time. I know velocity is the slope of a position versus time graph. All right. There are many ways we could do this lab. Okay. Let me tell you maybe 2 of them just to keep the video short. Okay. One of them is a lab that I do that takes advantage of this. It's a lab that kind of teaches you how to do this thing here. Actually, I lied. It's not that. It's that. It's this. It's a lab I do to teach this idea. Sorry, it's been so long since we've done it. So let me describe a situation to you. If I can get a data table or a graph of position time, so position and time, then I can graph it and look at the slope, and that'll tell me velocity. Okay. So I'm going to measure these 2 things. Perfect. These are my my variables that I'm interested in. These are the variables of the experiment. These are not control variables. These are just variables, dependent, independent. Okay. You can make either one dependent and independent, but what's important is that we need to graph them in this orientation, because this orientation is the one that has the slope is velocity. So we've thought about theory. We said, okay, one way I can find the velocity of something is by creating a position time graph and looking at the slope. Perfect. So how could I get these 2 variables? How could I measure these things? Let's start with the easy one, time. Okay, so the first thing that I need is a stopwatch so that I can time stuff. Okay. The second thing that I need is something to measure distance. All right, how about a measuring tape? Okay, so we stretch our measuring tape out. And then we put our toy car at the beginning. So we'll start it at 0. Okay. Then we are going to let it run. We're going to turn it on so that it's going at its constant velocity. And we're going to let it cruise along the measuring tape. And then there's 2 ways we could do this. We could either go 1 meter, 2 meters, 3 meters, 4 meters, and then record the times here. 1.2 seconds, 2.5 seconds, 3.7 seconds. You know what I mean? Record the times. And then I have this beautiful data table. 1, 1.2, 2, 2.5, 3, 3.7. And there we go. I've done it. Okay. So let's talk about how you should write that out. And I apologize. I wish I had maybe typed this out ahead of time, but bear with me. At least I won't write or talk too fast for you to write it down. So we need to describe the experiment. So let's talk about the setup first. Step 1, setup. Stretch a measuring tape out to let's say 6 meters to 6 meters and tape it to the ground. Okay. So far I've indicated I need to use a measuring tape. I'm going to put it on the ground. Okay. Set the car at 0 meters and allow it to drive along the tape, the measuring tape, that is. Okay, there you go. That's setup. Let's talk about step 2. What am I recording? Okay, so step 2 of a... Ooh, that's not a good color. Let's do this cayenne or whatever it's called. Or teal. Teal. Step 2. What do I record? As the car passes each meter mark, and you might want to like elaborate. If you're ever in question, will someone understand what I'm saying by this? Make it explicit, not like put an F word in here, but say like 1 meter, 2 meter, etc. Right? Like so that they know what you're talking about. Record the time. There we go. You told me what to record. I'm recording the distance and the time. And we might want to say with a stopwatch. Okay, just so that they know that we're not just counting like 1 Mississippi, 2 Mississippi. You know what I mean? We've got some accuracy. Step 3, what do I do with that? So plot the position on the y-axis and time on the x-axis and fit it with a best fit line. The slope is the velocity. Okay. So I've explained how do I analyze the data? What do I do with it? Do I put it into a formula? Do I graph it? What do I look at on the graph? I've explained what to do with it and where to look for the answer. Okay. Last step. How do I minimize error? So what are some things that could go wrong with this? Do you think that a car driving on a flat track would be different than a car driving up a ramp? Do you think it going up a ramp would have an effect on the velocity? Probably. That's one way. So we could say step 4 for reducing risk. Make sure the car is on a level surface. Okay. This next part this next sentence, starting here at this bracket, admittedly should probably go here because it's a little bit of analysis. The other way, do you think the car is going to do the exact same run all 3 times? Do you think a little $10 toy car is going to be that consistent? I don't. So you could also say, instead of maybe pointing out something about the setup that would reduce error, you could point out a methodology that could reduce it. Run the car 3 times and get averages for the times. This would help us reduce error. Maybe one time you put down the car and took half a second to start the timer, or maybe the car doesn't travel in a straight line, but one time it did a little bit better. Or sometimes it veers left and sometimes it veers right because the floors at Independence aren't very level. All of these things would be fixed if you did it multiple times and took an average. Okay? Because you're doing an average and then probably plotting the average instead, you should put it before the plotting, just so, like step 1, step 2, step 3, the order. So this would be an excellent free response essay for that question. How do I measure the velocity of a car? You told me, how do I set it up? What do I record when it's doing its thing? And 3, what do I do with that recorded information? Then you also told me a couple of ways that it might get goofed up and things I should just be on the lookout for, or things I can do to minimize error. Good job. I'm proud of you. All right. Let's talk about this one. This one is, I was looking on the AP site, and this is like a very simplified down FRQ, but it's still an FRQ. This is actually a thing they'll ask you on the AP test. So let's look at this one. So there's a bob hanging from a very thin light string, and you want to determine the period of oscillation of the pendulum. Describe a procedure you could use to determine the period. So let me tell you a couple of things about this problem. First of all, a bob just means like a heavy thing on the end of a string. It's just a weight. I don't know why they call them bobs. Okay. The period of oscillation is a vocabulary that we haven't talked about yet, but a period of oscillation is the time it takes to do a full there and back. Okay, it's how much time it takes for a round trip for the system to repeat itself. Okay, so let's look at this thing and then let's talk about how we could do that. So we're going to take this bob and we're going to pull it to the side and then we're going to let go. The period will be how long it takes to go all the way over here and then come all the way back to where it started. Okay. So this seems very straightforward to me. But the reducing error part is probably the most important part for this, because what they're asking you to figure out is the most straightforward you could possibly do. You need maybe 2 pieces of equipment for this, aside from what's already pictured here. Okay. Obviously, because they're asking us to find a time of something, we need a timer. Okay. What we're really going to focus on here is reducing the error. Okay. Let's talk about what are the 3 things that you have control of on this that could mess this up. The first thing that you have control of is how far you pull this thing sideways. Right? Do you think the amount of time it takes to go like that is different than the amount of time it takes to go like that? If you do, then you should just be wary of the fact that you need to pull this thing to the same angle every time. So you might want to put a protractor, one of those math tools that you have because physics teachers are math teachers, to make sure that you're pulling it to exactly 30 degrees every single time. So let's start our procedure here. Step 1. Use a protractor to pull the bob 30 degrees to the left. Okay, that's the setup of the problem. Okay, we've done this. I've told you I need a protractor, and I've told you maybe not how to use the equipment, but how to set it up. Okay, now we need to get that period. So we could let go and let it come back. I'll go 3, 2, 1, let go. You hit the timer. It swings, it comes back. I catch it, stop timer as soon as it gets all the way back, right? Ta-da, I have the period of oscillation. But let's talk about ways we could improve that to reduce error. So one way we could do that is we could let it go, let it come back, and then do that 10 times, and we'll average all the times. Here's a method that Dr. Culbertson would be proud if he could see me right now. Let the bob swing back. Let's see, not back. Away and return. Whoops, that's an R. 10 times. And record the total time using a stopwatch. Okay, hear me out on this. We have 10 periods now. And now we take the average. Here's the step 2 part. What do I do with that information? Divide the total by 10 to get the average. Whoops. Period. Beautiful. Okay. Dr. Culbertson would be so proud. If you guys go to ASU and study physics, tell him I said hi. Okay, what else do we need? So we've talked about the setup. We've talked about what do I record. We've kind of talked about the analysis part too. We've divided by 10, and that will be the average. Okay. We've reduced error by pulling the bob to exactly 30 degrees every time, and we've reduced error by taking an average. See, sometimes you don't need all 4 sentences. Sometimes 2 sentences will do if you have a simple enough system. Okay, so hopefully this has been helpful to you. I will give you some problems to work on. Don't worry, you're going to hate them. These only look simple because I know the answer already, right? Coming up with these procedures is actually the hard part. The hard part is finding the procedure to begin with, but you know what to do. All right. Thanks for watching. Have a wonderful day. Make sure you like and subscribe. Make sure you share this. I know you guys have homies at other schools that are taking physics. Be like, hey, yo, my teacher made this type video. Watch it. You know, send it to your cousins or something. Or show your no, don't show your parents. Don't show your Nah, don't show your parents. Don't show your parents. All right, make sure you like and subscribe. I'll see you guys next time.